Hello and welcome to this installment of AP Physics 1, Kinematics 105, which is about position and displacement. As we previously said, kinematics is a subfield of physics. It's about the motion of bodies and systems. We begin by describing the geometry and discussing the initial conditions. There are different types of motion that we will study, but ultimately we need to focus on position. Of the quantities we can measure position, we can measure time, and we can measure mass. But measuring position and time will allow us to determine, from these fundamental quantities, will allow us to determine these derived quantities of velocity and acceleration. So it all begins with position. The formula we are going to focus on is this one here, which is the change in position. This one is the displacement formula. So we're going to focus on that in the lesson today. So let's first begin by looking at the nature of space. Now, the nature of space can be represented on a piece of paper, and for many of you this may be the first time that you'll see such a thing, but this is actually what we would call 3D graph paper. It is also called isometric graph paper. And the way it looks is we can start out with one axis like this. That's one dimension. And then we have another dimension like this, our second dimension. And our third dimension can be drawn like that. Hopefully better. We'll do that one a little better. Now, this axis is the z-axis. This axis is either the x-axis or the y-axis, and this is the y-axis. This is our origin. So we have positive y and negative y, positive x and negative x, positive z and negative z. So whereas in the Cartesian system we have 4 quadrants, in three-dimensional space we have 8 octants. And so you might imagine then that we have our first octant that on this dimension is there. This is our second octant. Our third octant like so. And our fourth like that. So that is like the Cartesian plane with the quadrants. Now you can see then that there will be in the back this octant that's like a cube. And then in the front, we have this octant, and we have this octant going upward, and three-dimensional space, and this one. Well, that is all those above that horizontal plane. And there's another 4 below. So there are 8 octants. Now, for our purposes, we are going to focus today in on just really we want to visualize one octant. So what this origin here would represent, here's our z-axis, our x-axis, our y-axis. Here's our positive values. Is that we could picture this as the corner of a room. Look into the corner of a room, and that's what we're looking at. This is where 2 walls meet. And this is where the side wall and the floor meets. And this is where the floor and the other side wall. So that can help us visualize space. Now, we could locate any object with 3 coordinates. we can start out with in one dimension, we can specify its x-coordinate. So let's suppose we have some object that is depicted like this. Well, the first thing is this may be located that far along the x-axis. It may also be located this far along the y-axis and this far along the z-axis. I should have drawn that a little neater, like so. So we can see this is positioned about 5 units out the x-axis, up a certain number of units like so, and out from the corner like that. So we could describe it in 3 dimensions. But what we do in physics is we take something as complicated as 3 dimensions and break it down into 1 dimension at a time. So lest this get too confusing, we study 1 dimension at a time. And 1 dimension is a line. It's somewhere along a line. Our line could be along the y-axis. It could be along the x-axis. It could be at this value. It could be at this value. But we describe the motion in terms of a line. And we'll see a little more clearly in the examples we have on this page. So first, we've already in a previous installment defined distance as the length of something. It has magnitude, 5.6 meters. Position, however, has a different definition. Position is where a body is located. It is, in a word, the location of something. So that necessarily means it involves or includes a distance relative to some reference point. So there's more to it. There's more to it. And that position has both a magnitude, 5.6 meters, and a direction from the reference point. Position is defined simply as the change in position of an object. So, if we have the position of something given by x, then the change in position, the change in anything, is always the final state or the state at some instant minus the starting. And so change in position, position being x, change in position is delta x. So it is the position at one instant in time minus the initial. And again, we look at motion in 1 dimension. If motion is 2 dimension, a plane, we turn it into a line. And it turns out if it's in space, 3 dimension, we turn it into lines. And as we move through the course, we'll see how we do that. But let's first get a better understanding of the interrelationships between distance, position, and displacement. So let us suppose we have a body that is located at a position of 2. So we say that is its initial position. And it ends up at position 6. That is the position at 1 instant in time. So to compute the displacement, we are at 6 and we began at 2. The displacement is 4 meters. That's what delta x is. And we want to denote that we started at xo and we went to x. So this arrow indicates the direction of motion. Similarly, we could start here at a position of -6. And we can end up at a position of -2. And that is the instantaneous position. We draw an arrow indicating the direction of our motion. And to use our formula to compute that displacement, well, we ended up at -2 minus the initial position, which was -6, which works out to be 4 meters. Of course, you may be a little perplexed because you see that the displacement, the change in position in both cases, is 4 meters. We could also say, and we are less concerned about this in physics at this level, is that the distance was 4 meters. The distance was 4 meters. What's more important for us is that the displacement was 4 meters. Let's consider this a little differently. Now, let's suppose we start at a position of 6. That is our initial position. And we end up at a position of 2. That is our instantaneous position. Our motion is indicated as thus. And so to perform a calculation, we have our instantaneous position, which is 2, minus our starting position, which is 6, which gives us minus 4 meters. Minus 4 meters. We moved in the negative direction. Similarly now, let us start at minus 2. This is our x0. And we end up at minus 6. Our instantaneous position. Well, our instantaneous position is minus 6, and we started at minus 2, so that gives us a change in position of minus 4 meters. The displacements are equal in magnitude. They are 4, and the directions are the same. In all 4 of these instances, the distance is 4 meters for this one, and the distance is 4 meters. So we can see is distance does not involve direction at all. Position involves direction relative to a reference point, the 0 point. And the displacement uses direction in terms of the change in position. What we know, when we have a displacement of minus 4, we may not know where it is, but what we do know is it moved to the left, which takes us to some conventions that I would like to share with you. When we have a number line, we clearly have a positive side and a negative side. By convention, we generally say positive is right and left is negative. It is not wrong to define it differently, but that's what we would assume unless it's specified differently. We define positive as north and south as negative. We tend to define east as positive and west as negative and up as positive and down as negative. Again, we don't have to, but we just generally use that as a convention. So let us now consider 2 other cases. Let's suppose now we are starting at a position of minus 2. So that is our x0. And we end up at a position of plus 2. Well, that's our position at a particular instant. And we moved in this direction. So to compute the displacement, we have the instantaneous position of 2, and the starting position was minus 2, which gives us a displacement of 4 meters, positive 4 meters. Now notice this displacement of positive 4 meters is exactly the same as this displacement, positive 4 meters, and this displacement. What they all have in common is they move to the right 4 meters. We would also notice that the distance or the length of all of the cases we have considered are 4 meters. Lastly, you may guess that we would start out now at a position of 2. That is our initial position. And our instantaneous or final position for our point of concern is minus 2. To compute the displacement, we now have minus 2, which is minus 4 meters. So the displacement is minus 4 meters. Positions can have magnitude and direction. Are they located in positive or negative relative to the point of origin? Displacements also can have a magnitude, a number, and a direction, positive or negative. And this is what position, distance, and displacement are. Again, lastly, with distance, this distance was all 4 meters. Now you may understand or infer now that if we are dealing with directions that are moving on one dimension, the x-axis, it turns out that we can define position as x, as y, or as z, which means that we can have displacement in the x direction, we can have displacement in the y direction, and we can have displacement in the z direction. We will just usually refer to the x direction, but beware that those are also there. So that is our introduction to distance and displacement.